So, taking what we just learned about and how a positive or negative first derivative tells us about increasing, decreasing, what we can do is end up running this first derivative test that can give us all the information of our function, all of the intervals where it's increasing, all of the intervals where it's decreasing, based on a first derivative test. So, and with that, where it changes between increasing, decreasing are going to be important parts, which we can call relative extrema. These are also called local minimums or local minima and local maximums or maxima. So the image down here, I like this for this kind of zoomed in sense, which I was kind of talking about in that previous video. For right now, we're going to ignore inflection point, but I'll come back to that in the next one. But local maximum is this idea of if we're super zoomed in with our function, so say we were even right here, what I could see is that my function's increasing. It's getting taller and taller and taller. We haven't reached the peak yet. Then as I go up here, getting taller, taller, taller. So all over this we are increasing until I reach that peak. And then it starts going downward and we start decreasing. So because it switches on the left-hand side, we were increasing up to it and now we're decreasing out of it, it creates a local maximum at that coordinate. Then over here, what we have is we're decreasing, and if I zoom in, it's like we're decreasing, decreasing, decreasing until I reach that point there, and then we switch to increasing. So where we're changing over, we're reaching this lowest value, which is going to be a local minimum. So what we're going to do is try to find these relative extrema first, these local minimums and maximums. And how we can do that is we're looking for where our tangent line has a slope of 0. So these relative extrema, how we find them, actually, let's give a few names for this. So relative extrema, local minimums or maximums, same thing. These are also our critical points. So all of that leads to this idea that we're looking for where is the first derivative equal to 0. What's going to happen is that's going to separate where we're increasing, decreasing. Now, something we need to be careful of is we're also going to be careful of discontinuities. So we're going to keep those in mind. Be careful of possible discontinuities, because those could change between increasing, decreasing as well while not creating a minimum or maximum. So we're going to keep that in mind as we go through these. So these are our steps for the first derivative test, and I'm going to walk you through an example too. But first thing, find our critical values. In fact, let's just go through this step by step. So first step, critical points. Or even let's just do the x coordinates is really what we need. We don't need the y coordinates yet. So we're going to take the first derivative of our function. So that's going to be a 3x squared minus 4x minus 9. And what we want to do is see where is this equal to 0. And solve. I would try to factor this, but I think that's going to be unfactorable. So let's go quadratic equation. X equals negative b plus or minus root b squared minus 4ac all over 2a. Okay, so that's going to be a 4 plus or minus. And you know what, let's go ahead for decimals. Let's just do that. And using the Desmos scientific calculator for these. So makes it faster to edit, in my opinion. Okay, divide. We're going to go 4 plus square root 16 minus 4 times 3 times -9 all over 6. So a 2.52. And then we'll have the one with subtraction, which is a negative 1.19. Okay, so found our critical values. And now what we're going to do is we're going to make a table of test intervals and test values. So we're going to have a table with our intervals. And let's go ahead and call this our increasing decreasing table. That's at least what I like to call it. I don't know if anyone else calls it that. So the idea is those are going to be points where we're switching. I know right before this I said be careful of discontinuities. I didn't say this out loud. This is a polynomial right here. This is going to be something that maybe looks something like that. No discontinuities happening there. This is just a nice smooth polynomial. It's going to be differentiable everywhere. So we're all good there. So with that in mind, these values should be separating up, increasing, decreasing. So what I do is I like to think of a number line. So like we have this negative 1.19 over here on the left. Over here we have a 2.52. So what this means is that we're going to have 3 intervals, because these should be points where we're switching between increasing, decreasing. We just don't know how it's switching yet. So we're going to have this interval over here. We're going to be having an interval between the 2 values, and then we're going to have an interval that goes off to the right there. So making my table, I want to describe these intervals. So I have from negative infinity to negative 1.19. I have between the 2 values, so negative 1.19 to 2.52. And then my third interval is going from 2.52 to positive infinity. So I just summarized, kind of using that number line as a guide, these 3 intervals of increasing, decreasing. Now what we want to do is evaluate a first derivative for each of these intervals. So what I want to do is just choose a value for x that's in each of those intervals. And I usually go for a nice whole number. Doesn't matter what it is, it just has to be in the interval. So like with this one, I'm thinking -2. If 0 is in the interval, I really like grabbing 0 because that's usually a nice one to plug in. And then over here, it looks like 3 is a good number. So again, I could have gone like -5, 1, and 53 for that last one. As long as it's in the interval, we're all good. So now what I want to do is evaluate the first derivative at each of those points. So where we're at with this is that we're deciding the test values. That's what x is called here. So those are our test values. And we want to determine the sign of our first derivative. So with these, we don't even particularly care about the numerical value. We just want to know if it's positive or negative. So I want to look at first derivative at -2, first derivative at 0, and first derivative at +3. And then what I want to evaluate is if it's positive or negative. That's all I care about. So our first derivative function, just going back to what we found when we were looking for our critical values, that was the 3x squared minus 4x minus 9. So if I'm plugging in -2, I'll have a positive 4 times 3, so a positive 12, plus 8, so 20 minus 9. I'm getting a positive value out. And you could also throw this into a calculator to make sure you're on the right track with them. That's going to be positive. If I plug in 0, I'm getting a -9 out, so that's negative. If I plug in +3, let's see, a 27 minus 12, and then -9, that's going to stay positive because they're big enough. And what happens is that this directly correlates to increasing, decreasing based on if it's positive or negative. So we have increasing, then we're decreasing, and then we're increasing. So what we did is through that work and using the first derivative, we saw that our first derivative was positive here. So that means this interval, our function's increasing. When we have a negative first derivative, that means this interval's decreasing. And then for our last one, we saw a positive first derivative, which meant this was increasing. So the little sketch I drew seemed to make sense where we're going up, and then we're going to switch to decreasing, and then we're going to be going up. And then we even know where those turning points are occurring. And those are our relative extrema right there. So evaluate the sign change to determine if the point is relative maximum, minimum, or neither exist. So we have our intervals for increasing, decreasing. In fact, let's go ahead and collect that to the side here. So our function is increasing on the intervals from negative infinity to negative 1.19 and from 2.52 to positive infinity. Our function is decreasing from negative 1.19 to 2.52. And then in terms of relative extrema, so if I want to know about any local minimums or local maximums, and there could be multiple, I think kind of all the pictures we've seen so far, there's only been one, but the more squiggly a polynomial is, the more local minimums and maximums there are. So there could be many. Okay, so what I could do is bring through our values that like right here in between those two intervals, that's where x equals negative 1.19. And right between these two intervals is where x is equal to 2.52. So what we can see is that our function is increasing and then we're decreasing. So that gives me the idea of a maximum. We're going up and up and up, and then we're going down, 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 which relates to a local maximum. So that would be at x equals negative 1.19 based on how we're switching from increasing to decreasing. Then for our next one, we switch from decreasing to increasing. So we're going down and then we're going up, and that's going to be a local minimum. So to go back to our wording here, if relative, or sorry, number 4, evaluate the sign change to determine if the point is a relative maximum, minimum, or neither. And so with how we're switching from positive to negative and then negative to positive, that's showing us our local minimums, maximums. The case of neither is if it stays the same. If we have increasing, then increasing again, it's possible that it's an inflection point. It's possible it's a discontinuity. Those are cases we want to be careful of. Okay, so that's our process. Just to, I know this video is getting a little bit long, but just to kind of walk you through the process, and we'll do this more too, and I'll kind of show you as it goes faster, but start with the critical values. That'll lead you to your intervals. The intervals are the start of the table, and then what you're going to do is evaluate a first derivative within each of those intervals and just make note of positive, negative, which will tell you increasing, decreasing. And that will get you your intervals for where our function's increasing or decreasing. Then for local extrema, see how we change from increasing to decreasing, decreasing to increasing, and how that would form a shape that would give us our minimum or maximum. And that's our first derivative test. It really comes down to this table right here with our intervals and then test values and then evaluating those test values for positive, negative.